Hi, we will present precise well plate placing utilizing contact during sliding with tactile-based pose estimation for laboratory automation. Our goal is to place a plate of a few centimeters in thickness, called a well plate, commonly used in chemical and biological experiments, onto a well plate holder. To perform this task, the following issues must be addressed. 1. Although the holder's poses can be detected with markers, errors in detection and marker misalignment can cause shifts of more than a few millimeters. 2. The required accuracy is a millimeter to a sub-millimeter order because the height of the raised groove is a few millimeters and clearance between the well plate and the holder is less than 1 millimeter. 3. The holder, lightweight and not fixed to a desk, can move under even minimal external force, risking collisions that may cause breakage or chemical spills. To address these issues, we propose a well plate placement method with two key characteristics. We address the issue, 1, through the accurate estimation of the well plate pose using a tactile sensor. This allows us to minimize the impact of potential errors in marker detection. To address issues 2 and 3, we use a precise placing method in which the well plate is slid onto the holder while maintaining lateral contact with the holder's raised groove, aligned with its estimated orientation. This method ensures alignment despite the limited clearance and prevents the holder from moving, keeping it stationary throughout the placement process. Our task setup uses two holders. Importantly, these holders are not affixed and are able to move when there is an appropriate application of external force, such as when the well plate is placed onto a holder with significant force. The height of the raised grooves with the thick sticker is 1.4 millimeters. The clearance between the well plate and holder is less than 1 millimeters. For our tasks, we use an RUCO marker attached to a holder that is fastened onto the pillars of the holder. Here, we show the overview of pick and place. First, the holders for pick and place are initially manually arranged on the desk in random positions. Then, the robot detects the RUCO markers on holders A and B. Next, the robot moves to the position of the holder A, grasps the well plate, and moves to a height of 4 centimeters from the holder B with a tilted pose. Then, using the tactile sensors, the well plate pose is estimated, and the well plate pose is controlled to certain pose. Under velocity control to maintain smooth movement, the well plate is lowered towards the holder B. The robot slides the well plate along the surface of the holder. When the well plate contacts the raised groove of the holder B during sliding, the robot estimates the raised groove's direction. The force-torque sensor detects that the well plate has arrived at the groove of the holder B. The well plate is placed down onto the holder B. Here, we explain pose estimation of grasped well plate using tactile sensors. If the pose estimation of the well plate is not done, the edge of the well plate and the holder will not be parallel. As a result, the corner of the well plate does not contact the raised groove of the holder. To detect the pose of this edge, we first process the GelSight Mini RGB image into a depth map by deep learning. We then take the depth map and use the Canny Edge detector to find areas of high gradient in the map. Finally, we take the output of the Canny Edge detector and use the Ho transform to find a straight line in the image. The well plate pose is estimated, and the well plate pose is controlled to certain pose. As the result, the corner of the well plate can be in contact with the holder's raised groove. The placing technique consists of some steps. Insert one edge of the well plate at an angle to increase failure tolerance. Push the well plate into the holder without rotation to regress the holder's orientation. Using the estimated orientation and end effector position data, estimate the contact point PC. Use proportional angular control to orient the well plate while sliding and maintaining contact to complete the placing. Our robotic system features a 7DoF Franca Amica Panda arm. This robotic arm is equipped with a custom-designed parallel gripper. The gripper includes two vision-based tactile sensors, the GelSight Minis. A Leptrino force-torque sensor is mounted between the robot arm and the gripper. By using a depth map, it facilitates an accurate recognition of the pressed well plate's edge using the Ho transform. On the other hand, performing edge extraction using a Canny Edge detector on the raw image without the aid of a depth map only results in the extraction of the GelSight's black dots. This impedes the successful extraction of the well plate edges. We evaluate the accuracy of pose estimation, focusing on scenarios with and without considering the displacement information of the adaptive finger. Both roll and pitch accuracy improved significantly when taking into account the adaptive finger displacement. Disregarding this adaptive finger displacement information led to substantial roll errors, mainly because vertical finger displacement, rather than horizontal, significantly affects the object's pose calculation. The influence of this error on the placing is discussed in the following results. These videos shows our proposed method and simple placing baseline approach. The simple placing approach can only be successful if the pose of the holder is detected accurately. Despite using a low-pass filter to improve accuracy, there are slightly errors. This small deviation can be problematic, given that the clearance between the well plate and the holder is less than 1 mm. On the other hand, our proposed methods demonstrated a 100% success rate, highlighting their robustness against noise in the recognition process. This table shows the success number of the well plate placement on the holder B and holder B's translation and rotation displacement. The result of method C shows that the well plate placing was never successful without pose estimation using the tactile sensor. Even a slight tilt in the roll during the well plate placing caused the well plate to extend over the raised groove of the holder. The results of method D show that without estimating the direction of the holder's groove, the placing was never successful. This was because the well plate pose was controlled by admittance control to make the well plate parallel with holder B, but it reached the end of the holder B before achieving parallel alignment. The results of method F and G show simple placing baseline approach. The small recognition error can be problematic given that the clearance between the well plate and the holder is less than 1 mm. By using the adaptive finger, we were able to reduce the risk of damage to the gel site. By using our proposed methods of pose estimation and grooves direction estimation, we achieved highly accurate placement even when there were recognition errors in the holder poses. Additionally, the amount of movement from the holder during placement was minimal, reducing the chance of disturbing the surrounding environment. In this paper, we developed a method for high-precision placing of a well plate onto a holder for laboratory automation. Our method consists of two components. 1. The well plate pose estimation using tactile sensors to ensure well plate contact on the holder's groove. And 2. Placing utilizing contact during sliding with the holder's groove and estimating its orientation to realize sub-millimeter order accuracy and to prevent displacement of the holder. The sub-millimeter order placing task was realized with high accuracy with small displacement, even under noisy conditions.